Hello everyone, my name is Linus and I'm happy to present our work Semidefinite Relaxations for Robust Multiview Triangulation. Robust multiview triangulation is a classical problem in computer vision which appears at the core of many 3D reconstruction pipelines. The objective is to estimate the location of a 3D point given n observations from distinct camera views which are corrupted by both noise and outliers. As with most robust vision problems, it is intrinsically both non-convex and combinatorial in nature. But despite this, we show that the globally optimal solution can be found in most cases using semi-definite relaxations. In particular, we developed two relaxations. One based on epipolar constraints, which is relatively faster, but only works in low to medium noise scenarios. And we also developed one based on fractional constraints, which is slower, but works in all except very extreme cases. We will start with a brief introduction to semi-definite relaxations. The key idea is to write the problem in the form of a quadratically constrained quadratic program, or QCQP, which means both the objective function and constraints are second-order polynomials in the problem variables. We can then write the problem in matrix form as shown here. This is a highly general formulation which captures many geometry problems in computer vision, but it is in general non-convex. To relax the problem, we introduce a new matrix variable, capital C, equal to CC transpose. This lets us reformulate the problem as a semi-definite program, which has the advantage of being convex and can be solved efficiently with existing solvers. If the solution to the semi-definite program is rank 1, we can recover the global optimum of the original problem via a singular value decomposition, in which case we say that the relaxation is tight. When the solution has rank 2 or more, the relaxation is not tight and we are not able to recover the global optimum. However, it is still often possible to generate an approximate solution, although with no optimality guarantees. A key metric for the effectiveness of a relaxation is therefore the percentage of relevant problem cases where the relaxation is tight. We will now go into how to reformulate the robust triangulation problem as a QCQP. We consider the truncated least squares extension of the standard L2 reprojection loss function, for which we introduce binary inlier parameters theta I that equal 1 for inliers and 0 for outliers. The first difficulty comes from the fact that the reprojection loss function contains a fraction in the problem variables. There are two methods for dealing with this in the existing literature, and we will show how to extend both of them to the robust case. The first approach was developed by Aholt et al. In 2012, and it is based on reparameterizing the 3D point in terms of its n reprojections xi, which have to satisfy the epipolar constraints. By doing this, both the cost function and the constraints are second-order polynomials in the variables xi, so the relaxation is obtained by stacking the variables xi into a single vector, together with a variable representing the value 1. For the robust case, we start by adding the binary inlier parameters, but this is not yet on QCQP form, since the first term in the cost function contains a third-order term, which is mixed in theta I and xi. To get around this issue, we can use the fact that theta I equals theta I squared to move it into the L2 loss. We can also multiply the epipolar constraints by theta I, theta j, since the constraints don't actually have to be satisfied for outliers. Then, as a final step, we reparameterize the problem in terms of new variables yi, which equals theta I times xi, which leads us to a second-order formulation. To maintain the relationship between yi and the original problem variables, we also have to introduce a new extra constraint that theta I times yi equals yi. We can then obtain the relaxation by stacking all variables into a single vector as shown here. After solving the problem, we can obtain the final 3D point by first computing xi from the yi and then finding the intersection of the viewing rays of the inliers, which will now satisfy the epipolar constraints. While this approach works in many cases, one important issue is that points satisfying the epipolar constraints are not guaranteed to correspond to a single valid 3D point. In particular, the epipolar constraints are also satisfied by any xi which make all the viewing rays coplanar. As an illustration, in this example there are 3 views with 2 noise-free inliers and 1 outlier whose viewing ray is close to the plane spanned by the viewing rays of the 2 inliers. In this case, the optimal solution is to wrongly classify the outlier as an inlier and select the xi such that all viewing rays are coplanar, but not intersecting in a single point. To tackle this issue, we need an approach that explicitly parameterizes the 3D point. This brings us to the work of Cifuentes et al. In 2020, which instead directly tackles the fractional reprojection constraints. The method is a bit more involved, so please refer to the paper for details. But the main idea is to multiply out the denominators of the fraction constraints, and then reparameterize the problem in terms of the pairwise products between the reprojection variables and the 3D point variables, encoded as a Kronecker product. We also have to generate redundant constraints by multiplying each reprojection equation by each Cj. After that, the extension to the robust case follows in largely the same way as for the epipolar method. We introduce yi equal to theta I xi and include both y and theta in the Kronecker product. To test our methods, we simulate triangulation problems by placing camera views uniformly at random on a sphere of radius 2, with the ground truth point close to the origin. We run the experiments for 3, 5, and 7 views for both methods and for 25 and 30 views for the epipolar method. We leave out the fractional method in the latter case due to the large number of constraints causing memory issues. On the left, we show the percentage of cases where each relaxation is tight, along with the resulting estimation error. Note that both methods work well up to a certain noise threshold, which depends on the number of views and outliers. But after that, the epipolar method degrades in performance. In contrast, the fractional method remains tight in almost all cases. We also validate our method on more realistic scenarios by taking a high-quality structure from motion reconstruction and generating triangulation problems by selecting a subset of views and adding outliers by replacing matched point with random key points in the image. Finally, we'd like to comment on the use cases of semi-definite relaxations for robust triangulation and computer vision in general. Since the runtimes are slow, relaxation-based approaches are typically not suited for real-time use, unless the ability to certify global optimality is critical in the problem scenario. However, we argue that having tools for computing global optima can be very useful for debugging or profiling algorithms in an offline manner. For example, in order to establish the degree of sensitivity to local minima. Thank you very much for listening, and I'd be happy to answer questions either online or at our poster.